Here we go then with what is known as optimization. Optimization is one of the most talked about pieces of math, even though most people don't sit around and do any of the calculations associated with optimization. But we talk most often about what is the best something could be and what is the worst something could be, which is one of the reasons why mathematically, when we're studying functions or graphs of functions or sets of inputs and outputs about a function, we talk about the domain. The domain goes from the furthest left to the furthest right, and the range goes from the furthest down to furthest up, if we're talking graphically. And this relates exactly into how we as people think about things. We think about extreme scenarios, and that's actually, I think, a really useful way to approach a lot of situations because it allows you to think through outcomes. Now, I'm not saying extreme situations are likely to happen, but those are generally the things that we're going to be most interested in. So something that's a term that is a little bit out of season, but still fits in here is this idea of a 100-year flood. So what someone means by a 100-year flood typically is in 100 years, we would expect this place to flood to this level once. And it's kind of a way of talking about a probability. So 1 year out of 100. And then you have something like a 1,000-year flood. So 1 year out of 1,000, we might expect flooding to be this bad. And these are calculations. Sometimes they're based on data. A lot of times they're based on some combination of data and when I say data, what I mean by that is actually measuring flood heights and flows and all of that. And other times it's a lot of analysis. But regardless, what we're talking about in the case of flooding is what is the highest this flooding could get? And the reason why I like to talk about flooding is because it paints a really interesting picture for optimization. So if you're talking about optimizing an outcome, you could be talking about making it as really good or as really bad. And sometimes we want something to be really bad. What's an example of really bad? We would want a flood level to be really bad as in low. We don't want it to be really good as in high, or you switch those around. Other things you might think about are illnesses. We would like to minimize severe cases. So optimization in terms of language and English is very confusing and fraught sometimes and requires a great deal of consideration. So on to this classic problem. We're enclosing a rectangular garden with a fence. One side is along a house, so we won't be fencing. You have 50 feet of total fencing. What are the dimensions of the largest garden you can enclose? So this is a problem that you may have studied already. This is a problem you may not have studied already. Either way, we are going to study it. Wow, they have changed things on the Zoom. Interesting. So when it comes to these types of situations, the hardest part is the picturing process. And during related rates, I talked to you what I meant by picturing. Picturing in my mind is a mental picture, not you're drawing a picture mentally, literally, or you're drawing a picture literally on paper. You're trying to comprehend what a question is asking about and what it's looking like and what the answer is going to look like. So what we're talking about here is we're talking about having a garden, and the garden is going to have a fence on 3 sides. And it said it's going to be rectangular. So we know that a rectangle forces these 2 sides to be congruent. Everything is right angles, yada, yada, yada. The area of the rectangle is base times height. The perimeter of the rectangle is 2 bases plus 2 heights. All of these things are things that we know about rectangles, but the picturing process is about making sense of the information that we've been given. So what information have we been given? We've been told that we have 50 feet of fencing. And it's really helpful to think about all of these things. Sometimes it involves writing it down. Sometimes it doesn't involve writing it down. It's just talking it through or thinking it through. Some of you may need to do almost no picturing to make sense. Everybody does picturing to some extent. So before I try to proceed with like actual math, which is what most of you call problem solving, even though I would say we've done math already. But the actual math part is I like to know what my answer is going to look like. So dimensions. I can be more specific than dimensions, can't I? Specifically, base and height that maximize area. Oh, I forgot to mention, I'm sorry. Copies of these problems are available on the PowerSchool page already. So when I'm done, I'll have a base measurement and a height measurement that corresponds to the largest area possible. Okay, noted. So like, how do I do that? How do you do that? Well, if you've done this problem before, you might have done something like this. You might have said that, okay, we're going to call this measure X and this measure Y. So the area is XY. The perimeter is 2X plus Y. What do you mean 2X plus Y? What I mean 2X plus Y is we're only doing one of these. Right? Because the other one is along the house. So how does the 50 feet of fencing fit in? Well, we could say that 50 equals XY. And 50 equals XY is not terribly helpful because we have two variables in the same equation. That means we could solve for X. We could solve for Y, but in neither case are we able to determine a value of X or a value of Y that will work here. Oh, wait, you know what? 50 doesn't represent area. We don't actually know the area. My picturing was wrong, wasn't it? 50 is the perimeter. Okay, so that's a little bit more interesting maybe. I mean, I can do the same thing, right? I can solve for X and Y, but it doesn't actually solve for X and Y. What I mean by that is I don't have a value for the X length or a value for the Y length. But using what I know about math, substitution, in this case, I could say that the area function of X equals X times the quantity of 50 minus 2X. And in a pre-calculus world, this is an imminently solvable problem. What do I mean by that? Well, we're maximizing a parabola, which is code for, get the vertex. Okay. So I've got the area, which is a negative 2x squared plus 50x. And there's lots of ways of doing this. What I would like to review with you, though, is completing the square. Oops, didn't make that big enough. So there's two blanks there. There's a plus and a minus. So what's going to go in this blank is the value that completes the square. What I mean by that is we take our value of b divided by 2 and then square it. Why do we do that? Because it allows us to factor oops, there's no x there. This thing as a perfect square trinomial. So 25 divided by 2 and then squared. That's a 625 divided by 4. Something else you may be wondering about is why did I add and subtract? Well, I can only add 0, correct? Yeah, if I add anything other than 0, I've changed the value of the problem. So by adding the same thing and its opposite, I'm adding 0. That's what I'm doing. Okay, so we have negative 2 times the quantity of x squared minus 25x plus 625 divided by 4 plus 625 divided by 2. Where am I getting 625 divided by 2? You'd be asking yourself if you were actively involved in math. And this is one of the reasons why it's so much harder to do math without a teacher, because the teacher is doing all this explaining for you and you're not having to find the explanations. But what I did was I multiplied negative 2 by negative 625 over 4. And the reason why I did that is because this thing right here is going to factor now. That thing is going to factor perfectly, hence being a perfect square trinomial, into x minus 25 halves quantity squared. And I've got plus the 625 over 2. And that is, of course, my area function. So I know the x value that maximizes the area is 25 halves. And the area is 625, I'm sorry. Yeah, 625 halves square feet. So honestly, all we're missing is the y value. And there's a couple of ways I could get it. I could do 625 divided by 2 equals xy. Substitute for x, y is 25 feet. Realized I didn't finish my thought up here. Okay, so all of that without a lick of calculus. So what does this look like if we do it with calculus? Well, a little bit different. Maximize area. That's where we start out with calculus. Everything up to here is the same. If we want to maximize area, the derivative of area equals 0 or does not exist. That's what we want to do. Okay, so how do we do that? Well, a prime of x. You could either use the product rule here, Or you could just do the derivative for this one. It doesn't matter. You get negative 4x plus 50. X equals negative 50 divided by negative 4, which I can simplify into 25 halves. Nice, they match. Look at that. Now, because we are maximizing, the other piece of calculus is we got to remember all possible values. Include the endpoints. Now, because we did the pre-calculus already, we know that this is going to be the answer. But discussing endpoints is definitely a useful mathematical exercise. So what we do is we say, okay, what's the value of x that's going to make this equation, or the least value of x that's going to make this equation possible? Well, we can look at the picture for this. How small could x be? Could x be 1? Sure, x could be 1. Could x be a half? X could be a half. Could x be a fourth? X could be a fourth. Could x be an eighth? Yep. A 16th? A 32nd? A 3200th? A 1 billionth? Yep, all of those are possible. So what do? Well, we cheat. We use mathematical notation to say that we're considering the open interval starting at 0 because we approach but never reach 0. And we do the same thing when we think about what's the largest x could be. Well, the largest x could be is 25. Why 25? Well, because if these are both 25, then that means, or approaching 25, then that means y is going to be approaching 0. So even though we've got a specific interval of values to consider, there's really only one that's possible. And we know that because of the extreme value theorem. And this is part of the review bit. The extreme value theorem tells us for a continuous function on the closed interval. So that's why I don't need to consider my endpoints, even though I'm actually looking for the most extreme value possible. So this is a good place to pause. Check in. We're going to pick up with something again that I forgot to do for number 1 as part of the calculus. All I can plead is extreme out of practice-ness. You're not the only one who was on a long break. Sorry about the mistake. So if we're talking about showing a maximum, it's not just enough to show where the first derivative is 0, because it could be a minimum. It could be neither a maximum nor a minimum. So what we need to do is we need to make sure we lock it down. So if I use my interval from 0 to 25, I know that I don't have to test 0 and 25, which I mentioned, but 25 halves, I do want to make sure that this is a maximum. I need the sign to change from positive to negative. So what I did was I considered a value between 0 and, this is about 12.5, 10 here, and I said that that's going to be bigger than 0. So the derivative is positive. Then I considered a value between 12.5 and 25. I did 15. Just going to be negative. So on this interval, the first derivative is negative. And then I made sure to write out my math correctly. So at 25 halves, the first derivative changes sign from positive to negative. So the area is at a maximum. And then I finished my argument because it didn't just ask for a relative maximum, which is what this first part is. So this first part right here only establishes a relative max. It does not establish what we need to show an absolute max. But I can show that this is an absolute max just by explaining that this is the only maximum. Since that's the only maximum, that's the only one that we could possibly consider. So that ends this, our first classic example of optimization. I'd like to share another classic example of optimization with you right here. So like I mentioned before, this file is available in PDF form on the PowerSchool page, but I'll read to you. So we're making an open top box from a 12 by 18-inch piece of cardboard. And what we're doing to make that open top box is we're going to cut equal-sized squares from the corners and folding up the sides. Find the height of the box with the largest volume. And that doesn't make a whole lot of sense, I don't think. Why would we want to find the height of the box? How does that help? Well, what's indicative, I think, is this picture over here on the right, the one with the dotted lines and all of that business. So if it helps to draw a picture, you draw a picture. If it doesn't help to draw a picture, you don't draw a picture. All we're trying to do, though, is picture. And again, what I mean by that is make sense of the problem. So what we're thinking about here is an open top box. So that's the thing on the left. And we want to find the height of the box with largest volume. So what does that mean? Now this can be done without calculus, but we are only going to do it with calculus. So let's think about what this means. If we want height with largest volume, what we want to do is maximize, or if you prefer the term, optimize the volume. So what we're doing in terms of calculus is find the height that makes volume largest. Okay, so what does that mean? That means the volume is going to have to equal 0 and change sign from positive to negative. And we have to look at the endpoints. Once again, this is in reference to the extreme value theorem. The extreme value theorem says a function will have an absolute maximum and an absolute minimum on an interval, a closed interval where a function is continuous. Okay. So this is all part of the picturing process. And some of you are like, we haven't done any math, all we've done is write. But remember, we're looking at math 5 ways in calculus. We're reading it, we're writing it, we're sketching it, we're calculating it, and we're interpreting what's going on. So this is all part of the picturing process. So what's going to happen here is we're going to cut corners. Feel free to make whatever obligatory jokes you'd like with cutting corners. We're only cutting corners to make the box. We're not cutting corners to do the math. And then what happens when you cut out the corners is you can fold right here. That flap folds up. Same thing here. And then same thing here. All of these flaps fold up, and then we've got a box that's open on top. So that's what we're doing. And this part right here is the height because of the flaps. So now that we have a really good understanding of the situation, we kind of run into what ends up being often the hardest part of doing optimization. What's the volume? Not what value, but we're trying to maximize the volume, which means we need to find the first derivative of the volume. Well, we don't even have the first thing to take the first derivative of. And that's what presents the complexity oftentimes with these optimization questions. So how do you do volume? Well, volume of a box is the area of the base times the height. Okay. So what is the area of the base? Well, it's a rectangle. So we need the area of a rectangle. And how about the height? Well, the height is something that we just don't know. So the height, I'm just going to call h. Often this ends up being x. Okay, nailed it, right? Got the volume. We don't have the volume. All we know is that the height is h. We have no idea what the area of the base is. I know the area of the base is a rectangle, but that doesn't help me much because I don't know the dimensions of the rectangle. I know that this isn't 12. The most it could be is 12, right? Because 12 is the piece of cardboard or whatever it is we're working with. I don't know what that length is unless I think about it. So it's not 12, it's smaller than 12. And how is it smaller than 12? Well, because we're subtracting out 2 cuts of the height, right here and right here. So that length right there is 12 minus 2h. Again, why is it 12 minus 2h? Well, the total is 12, and we're cutting right here, which is h, and we're cutting right here, which is h. So it's the whole thing 12 minus this h minus this h, or 12 minus 2h, which is actually really helpful because it allows us to say that the other measure is 18 minus 2h for the same type of reasoning. The total length is 18. We're cutting here and we're cutting here. So we're not doing all the way 18. We're doing 18 subtract this and 18 subtract that. So the area of our base is 12 minus 2h times 18 minus 2h. So we already know the calculus here. We know that we need to take the derivative. But taking the derivative here is a little bit fraught because it's a 3-thing product. Now you can take the derivative of a 3-thing product rule. It's a little bit complicated because you'd use the product rule here. So you do the derivative of this times this plus this times the derivative of this. But to take the derivative of this, you'd use the product. I'm actually going to skip that and I'm just going to distribute. That is, if I can remember. I can't. I don't remember what 12 times 18 is. Feel free to make fun of me if you must. So 216 minus 24h minus 36h plus 4h squared times h. So 4h cubed, that's 60 with a negative h squared plus 216h. So the derivative is not bad. It's 12h squared minus 120h plus 216. We want to set this equal to 0 and solve for h. And then we want to think about endpoints. So what's the most h could be? What's the least h could be? All of that jazz. And that's how you would end up solving this. But we're not going to take this all the way. This is enough for the calculus for what we need to do. Honestly, the calculus for what we need to do is conceptually and oftentimes the part that is easiest because it's the part we've done the most. All of these different situations are a little bit unique. And because they're all a little bit unique, we don't have as many repetitions and they feel harder. And it also feels harder because it's not going to be step by step. There's no recipe. There's no recipe that's going to do it. Third and final classic optimization question. So we're doing classical mathematics today. I'll let you read it to yourself. And while you're reading it, try to picture it. Okay. So I hope you enjoyed that processing time. I'll read it quickly. A company currently sells 60 gift sets per week for a price of $90 each. Their market research has shown that for every $6 drop in price, their sales will increase by 12 gift sets per week. That part right there is always the part that to me feels like a little bit of massaging of the data, if you feel me on that. It's similar in my mind to all of those math problems where some schmo goes to a store and buys 8 bajillion watermelons and 17 grapefruit, and his friend bought 17 watermelons and 8 bajillion grapefruit, and they don't know how much each one costs. Those are, I think we can agree, pretty contrived situations. Yes, no? Yes. 100% yes. Those are contrived. So in this sense, this problem is a little bit contrived. But either way, it's going to allow us to take a look at optimization. which is going to be pretty fun, I think. So the picturing process here, kind of hard to draw a picture, right? Yeah. How do you draw a picture of something like this? That's why I still use the picturing process, but I don't mean picturing literally. So what we're trying to do is maximize revenue, which means we want a revenue equation that I can take the derivative of, set equal to 0, look for a sign change for positive to negative, check endpoints, make sure I'm good to go. And here is where we're still doing math, even though you don't think we're doing math, because we are not calculating anything, kind of. You may not know what revenue is. Well, revenue is how much money you make. And if you're selling widgets or whatever it is we're selling here, unobtainium, flirtagibbets, who knows? However many you sold times however much money you make, that is what you got. So 60 times 90, that's what we got, right? So we sold 60 items, 90 monies per item. Okay, so we've got whatever that is, $5,400. Right, that's our revenue. Now, market research, again, the contrived part, market research says that we're going to sell more if we decrease the price by $6. That's not the forced part or the weird part. Okay, that would make sense, right? If you decrease your price, you're going to sell a few more. Most people are going to do that. But here's what's interesting. There's going to come a point in time where you can't decrease your price anymore because you won't be making any money. Those things cost. They cost materials, they cost labor, they cost stuff. So you can't just say, well, we're going to sell it for 0 and then we will have infinitely many monies coming in, because that's not how that works, because you're selling it for $0. So your revenue is $0. Hopefully that makes sense. So let's see what happens. If we decrease the price by $6, that means we're selling it for 84 bucks. But we're selling 72 items. So our revenue is going to be 84 times 72, which is nice. It's more. It's 6,048. Okay, that worked so well. Let's do it again. Let's decrease by another $6. So now we're at $78. And that means we sold 12 more, right? So that's 84. That was pretty good. That's 65.52. So you may be thinking to yourself correctly, Mr. Lepkowski, we are not doing any calculus. We haven't taken a derivative, set a derivative equal to 0 and thought about endpoints. You're right. Could you solve this using the guess and check brute force method? Yes. Should you solve this? The answer is no, this is calculus. So don't do this to solve. We're not guessing and check. If you guess and check, you get 0 puntos. Okay, great. But we can still take time and figure out what's going on. So what is going on? Well, we subtract 6 and we add 12, and then we subtract 6 twice, and we add 12 2 times. So if we did that again, we'd subtract 6 3 times, and we'd add 12 3 times. Oops, that should say 2 and that should say 3. That's what we're doing, yes? Yeah. we could subtract 6 4 times and add 12 4 times. And we keep going like that. Seems to me like we have a pattern, yes? So x is going to be the number of times we do the thing. Okay. And, oop, that should say monies. Okay, got it. So if we decrease x times, we sell 60 for $90. If we decrease 1 time, we sell, oops, that's backwards. That is 90. Sometimes I hate writing. All right. So if we don't change the price, or we won't change the number of items sold, correct? Correct. Okay. So we sell 60, we make 90 each. If we decrease the price once and we sell more, that's 72, and this is 84. If we do it twice, this is 84, and that's 78. So what we're looking for here is patterns, because patterns allow us to use variables. So what's the pattern for the number of stuff sold? It's 60 plus 12, but not just 12, 12 times the number of price reductions. Okay, how about the monies? Well, the monies are going down, but the total monies are going up. So the monies are going down by 6 each time we reduce the price. So check it out. If x is 0, I get 60 and 90. If x is 1, I get 72 and 84. If x is 2, I get 84 and 78. If x is 3, according to my equation, I'd predict 60 plus 36 is 96. And 90 minus 18 is 72. Well, let's follow along. I'm subtracting 6 here. 78 minus 6 is 72, check. I'm adding 12 here. 84 plus 12 is 96. So revenue is 60 plus 12x times the quantity of 90 minus 2x. I'm going to use the product rule this time because it's been a while. But you don't have to. You could multiply. $90 times 12, 1,080. Okay. From here, I'd want to do a sign change, show that the sign changes from positive to negative. I'll save you the trouble, tell you that it does. That allows me to conclude that I have a maximum at x equals 20. What is the maximum at x equals 20? Well, I could figure that out with the revenue equation. That's just fine. But I would also want to talk about endpoints. So what are the endpoints here? Well, we could do 0 price reductions, right? 0 price reductions. That is possible. What's the most price reductions we could do? That doesn't make sense, does it? 6 times 20 is 120. We definitely couldn't do that, could we? Most we could do is 15. Oh, it's because I'm a bonehead. I changed that -2 to or the -6 to a -2. One day I'm going to grow up and turn into a math teacher. Maybe you'll be here for it. Sorry about that. That seems much better. Okay. So same thing, show a sign change. Think about the endpoints. So I could do 0, right? 0 would make sense, 0 price reductions. Could I, and then the most I could do is up to 15, but not including 15. Like technically it's 14, right? I mean, I guess I could do 14.5 price reductions. But I could see a pretty credible case here for the endpoints being 0 to 14. Like that would also be fine. Regardless, when we substitute 5 into the revenue equation, that's going to be the largest possible revenue. And that's our third classic optimization question. So what are the takeaways from optimization? Well, the first thing, and is probably the hardest thing, is the picturing process. So how does the picturing process go? Well, you read and reread, right? Because when you're doing it on your own, you don't have me reading and thinking for you. You have to connect to prior math knowledge. This right here, that's typically the hardest part. What prior math knowledge am I going to make sense of? And then finally, almost as hard as the one I just started, is know what your answer looks like. So if you were curious about how I figured out 20 was not right, I figured out 20 was not right literally the way I discussed it. I said if I do 90 minus 120, get negative 30. I don't think I'm going to be able to run a profitable business if I'm giving somebody $30 to take my thing. That doesn't sound like I'm going to make a lot of money with that. So knowing what your answer looks like is helpful. What are some examples of knowing what your answer looks like? Well, knowing what my answer looks like here was determining a price. And here it was going to be determining, oopsie, sorry. For the second one, that was determining a height. And then for the first one, I needed dimensions, base and height. How about prior math knowledge? Well, I'm talking about a rectangle, so I know about area and perimeter of a rectangle. I'm talking about the volume of a rectangular prism, which I know is the area of the base times the height. And then here, revenue is number sold times money made. So those are what I mean by connecting to prior math knowledge and knowing what your answer looks like. So once you've gone through the picturing process, it feeds into writing an equation. Why do you need to write an equation or make a model? It's because you want to finally get to the calculus. Okay, so what is the relevant calculus? It's these two pieces. The calculus part is, in my opinion, the easiest part. It is the remembering things part. You're going to take the derivative of a function, and it's generally not too bad of a derivative. So it's not going to be one of those triple chain with arctangent and natural log inside. It's remembering that you can show a function has a minimum or maximum when the first derivative changes sign from positive to negative and negative to positive respectively, or a second derivative at a critical value, the second derivative is positive or the second derivative is negative. When second derivative is positive, you have a relative minimum. When second derivative is negative, you have a relative maximum. I know that saying it's a three-step process is oversimplifying. This is why I don't believe in doing math with steps.